Hey guys, Ms. Maruzik here, and in this video we're going to talk about reversible reactions and how they can reach a state called equilibrium. Now, up until this point, we've really only talked about reactions happening in one direction, and so we've used stoichiometry to do those calculations. And for a long time, scientists only thought that reactions did occur one way. The problem is we can't see what's happening down at that molecular level to really see if things are going one way or two way. But due to some experimentation that was done, eventually scientists did figure out that there are certain reactions that can happen both directions, and so we call those a reversible reaction. Now, in a reversible reaction, the forward and reverse reactions are occurring simultaneously. So what that means is that if I put my reactants together, at some point, I'm going to start making products, but then those products are going to go back and start making reactants. So the two directions are occurring at the same time. Over time, though, what will happen is that those two rates, that forward reaction and the reverse reaction, are going to equal out. And so that's where we're ending up talking about equilibrium here in just a moment. Now, we denote a reversible reaction by using one of these two-way arrows, and depending on the problem you look at will depend on which of those symbols that they're using, but they all represent a reversible reaction. And if you think about it, we actually saw those back when we talked about reactions involving weak acids and bases. We said that those reach an equilibrium, and so we use those two-way arrows. So if those look familiar, they probably should. Now, it says here that some reactions are more likely to be reversible than others. And it gives us kind of a list here of some of the more common things. Reversible reactions tend to be things with insoluble salts, and you're like, wait, if it's insoluble, how can it dissolve? Well, we've kind of lied to you. Insoluble salts actually do dissolve an itty-bitty little bit. Not enough to make a huge difference, but we will be working with them in this unit with regards to equilibrium. And then, of course, as I mentioned just a moment ago, weak acids and weak bases. However, irreversible reactions, ones that tend to be only in one direction or mainly in one direction, are soluble salts, strong acids, and strong bases. Now, this is by no means like an all-inclusive list. There are some things that may fit this list and some that don't, but this kind of gives you a general idea of what things are typically reversible processes versus ones that are not. Now, it says here that all reversible reactions will eventually reach what is called equilibrium. And if you notice, this next part is in big bold letters here. So this is kind of important. It says equilibrium is the point at which the rate of the forward reaction is equal to the rate of the reverse reaction in a reversible process. So again, as I put my reactants together, initially I'm going to be making a whole bunch of product. But at some point, as that product starts to collect, I'm going to go back and start making reactant. And so at some point, those two processes equal out. But I want to call your attention very carefully to the fact here that we're emphasizing that only rates are equal. A common misconception is that amounts have to be equal at equilibrium. And that's not the case. It's simply just the rates that are equal. And we're going to talk more about that as we go through this unit. Now, it says here some important things to know about equilibrium. It says at first, the reaction looks like something's happening. Again, you have all those reactants and they're forming products. But at some point, those changes become less and less noticeable because now my products are starting to go back and form reactants. And I don't notice that change as being as significant. So to our eyes, at some point, when we've reached equilibrium, it's going to look like it has stopped. It really hasn't stopped on a molecular level, but it looks stopped to our eyes. So we have to be really careful about saying that, oh, this reaction looks done. Well, just because it looks done doesn't mean that on a molecular level, things still aren't changing. It might just be that it's reached its equilibrium, and so it looks like it's stopped. To kind of give us an idea about this, I gave you kind of a container here that has a level of water in it. And imagine that I'm putting water into this container at the same rate I'm taking water out of it. Well, if I look at with my eyes and I don't see what's getting put in and what's getting taken out, it looks like that level of water is staying exactly the same. It looks like the water isn't changing. However, if I could look at a molecular level, I would see that new molecules are going in and old molecules are leaving. So the process itself is dynamic. There's still changes going on, even though to our eyes it doesn't look like anything is happening. Okay. Now, you notice here that they give us kind of two graphs. These graphs might look a little bit familiar because we talked about them back in kinetics. So with this one, we have a rate and time graph. And so you notice if I'm comparing the rates, initially the forward rate is happening really fast. But again, as I use up those reactants, that starts to decrease. But then the reverse rate, products going back to reactants, at first is not at all, but then it starts to increase as I start to produce those products. Once I start to produce those products, then they can go back and form reactants. Now at some point, those rates will equal out. And so you notice here they blend with each other at the end of this graph. However, I want to show you this next graph here. This next graph, instead of rate, has amount, and you could replace amount with even a concentration. And you notice our reactants start really high, our products start really low, and at some point those are going to kind of switch positions here. Now, if I was to go take the slope of these graphs, that's what we did when we did kinetics. We looked at how the amount changes with time. But what happens is at some point, those concentrations level out. And once they have leveled out, then we would say we're at equilibrium. But you notice for this graph, the amount of products and the amount of reactants are not equal to each other. They're different. And that really depends on what reaction we have, if the reactants are greater at equilibrium or the products are greater at equilibrium. So let's look at some examples here in our next pages where we can see that sometimes I have more reactants, sometimes I have more products at equilibrium. It just depends. So let's go ahead and flip the page. And we see here that they give us an example. The Haber process is a reaction which nitrogen gas and hydrogen gas react to produce ammonia. And you can see that they've given us the balanced equation for that process here. And then it says that the concentration of all three substances is monitored over time in a closed system. The following diagrams were produced from two separate experiments, both conducted at the same temperature. So you notice here that in experiment 1, we started with lots of H2 and N2, and then we let that reaction proceed. However, on experiment 2, we started with lots of NH3 and let that experiment proceed. And you see that we kind of end up looking the same at the end. And so we're going to talk about that as we answer these questions down below. So the first thing they ask us to do is on each graph to draw a vertical line to indicate the time at which equilibrium has been reached. And so as we talked about on the previous page, what I'm looking for is when those concentrations level out. So I've kind of approximated the time at which I felt like that those lines flattened out. Now keep in mind, just because they flattened out doesn't mean the reaction has stopped. You notice that this has a two-way arrow involved, which means it's a reversible reaction, meaning it can reach equilibrium. And so what's happening here is at these points, we're now in equilibrium. So there's still changes going on. Products and reactants are still forming. It's just that they're doing so at an equal rate, and so the overall concentrations don't look like they changed. Now it says for experiment 1, did it travel in the forward or reverse direction? Well, as we mentioned just a moment ago, experiment 1 started off with lots of reactant side that went down, and then our product went up. So what we must have been doing here is moving in the forward direction, because we started with only reactants. However, on this second experiment, you notice we started with only product that it decreased over time, where our two reactants both increased over time. So here, this is going in the reverse direction because we started with only products. Now, I know some of you are thinking, well, if you're moving in the reverse direction, don't the products then become the reactants? And yes, they kind of do, but when I refer to what this equation is showing, that NH3 is on the product side. So we still refer to it as a product, even though the reaction is going in the reverse direction. I know that terminology gets a little bit awkward there. Now it says on the next question, did experiment 1 and 2 end the same way? And explain. Well, if I look at the end of these graphs, okay, where we've reached equilibrium, notice that they both look roughly the same. And so even though these two reactions started off very differently, in the end, we ended up with the N2, the H2, and the NH3 in the same ratios to one another. However, look at this next question very carefully. It says, when equilibrium was achieved, did the three concentrations equal each other? Well, if I look back at this graph, I notice that I ended with a lot more H2 and a lot less N2, and NH3 was kind of somewhere in the middle. So obviously, these did not end in the same amount. So while the rates were equal at the end, remember, at equilibrium, only rates are equal, not concentrations. We have to be really, really careful on that. Now, obviously, I could express the ratio of products and reactants when I reach this equilibrium. Since they weren't equal to each other, I could set a ratio of one to the other. And that's something we want to regularly do for reactions. However, we need to make sure we're doing so in a consistent format. And so that's where our next section comes in here with reaction quotients. Okay, it says to measure the extent that a reversible reaction has progressed, scientists agreed on a ratio of products to reactants called the reaction quotient. Now you notice they use this symbol of Q here for the quotient. It has a subscript of C because we use this in terms of concentration. Typically in molarity is the common unit that we use. And it says here that the reaction quotient can be determined at any point of a chemical reaction, meaning you could calculate the ratio of products to reactants at the beginning, you could calculate it a few minutes in, or you could calculate it once you reach equilibrium. You could calculate it at any point in a reaction. And so therefore, since it's not constant, it's not consistent, we can't report that value in tables. And since it's just a ratio, there are no units, which is very convenient for us, especially when we get to our math here in the next couple of days. So it says here that a reaction quotient can be determined using the following equation. And that is that our reaction quotient is equal to the concentration, you see those brackets there for molarity, of products over reactants, but you notice that they're raised to their exponent of a coefficient. So for example here, we have a reaction where we have some coefficients, we have some reactants, we have some products, and we notice that they use a two-way arrow, which means that this reaches equilibrium and is reversible. And so what we want to do is we want to write a reaction quotient for this. And so our two products are C and D, and so I would put their concentrations on top, but you notice here they're raised to exponents of 2 and 4. Those happen to correspond to the coefficients that they had in this balanced reaction. On the bottom here in the denominator, we have A and B. Those were my reactants, and again, they're raised to their coefficients. So it's not a hard formula to use. It's just we want to be consistent on what ratio we're using, and so that's why we want to use this set formula here. Now, something to consider is the fact that most of the time, I don't care about the reaction quotient at the beginning or the middle of an experiment. I really care about what the reaction quotient is at equilibrium. And so when the reaction quotient is at equilibrium, we give it a special symbol. So that's where we would call it then at that point an equilibrium constant, or K with a subscript of C. Now, I know some of you are thinking, wait a minute, haven't we seen a K before? We have, and we talked about rate constants. So we have to be careful. With rate constant, we used a lowercase k. Here, this is an uppercase K. However, the C is there because we're referencing concentration. So this would be the reaction quotient, that ratio of products to reactants, once equilibrium has been reached. And this is really, again, when we truly care about that ratio. Now, you notice the formula is exactly the same because, again, the Kc is the Qc when we're at equilibrium. So, therefore, the formulas should be exactly the same. Knowing what the Kc value is can tell us a lot of information about the conditions of that reaction at equilibrium, based on if it's larger or smaller than 1. So to kind of get into that, first off, as we've already mentioned, Qc can change over the course of the reaction. The value is dependent on the progress of the reaction. So what that would mean is that if I looked at the Qc at the very beginning of the reaction, it would be different than the value I have in the middle. It would be different than the value I have once I've reached equilibrium. However, once that Qc kind of stops changing, once it stabilizes out, then that's where we know that we've reached equilibrium. And so at that point, what we can say is that the equilibrium constant is equal to that reaction quotient, that they're one and the same at that point. And so at that ratio, you might have more reactants or you might have more products. It just depends on the specific reaction you have. And so depending on if you have more or less of one or the other, that can affect what value you have for that ratio at equilibrium. Now, it does say here that equilibrium can occur at any point in the reaction, and it is unique to that particular reaction where it does reach equilibrium. So like some reactions might reach equilibrium within 10 seconds. Some might take 5 minutes to reach equilibrium. Some might take 2 hours to reach equilibrium. It just depends on the reaction. Also, once I get that Qc value, it is unique for that reaction and at those temperature conditions. So every reaction has its own Kc value that's unique at those temperature conditions. Now, one last reminder, again, equilibrium does not mean amounts are equal, only the rates are equal. And so that's why we're going to have Kc values that are more than likely not 1 because the products and reactants are not equal. So now let's talk about math for a moment. Let's say that I have a K value that is larger than 1. Well, if I think about the setup of that ratio, to get a Kc bigger than 1, that would mean that the numerator would need to be bigger than the denominator. And if I think about the setup of that ratio, the products are in the numerator. So that would mean that products must be greater than the reactants at equilibrium. And so another way that we can word that is that equilibrium lies to the product side. Or we can say that products are favored in that equilibrium. Depending on the wordage of the question will depend on how we respond to it. If our K value is somewhere between 0 and 1, meaning some sort of small decimal number, that would indicate that the denominator is bigger, and of course the reactants are in the denominator. So that would mean reactants are more numerous overall than the products, and so we would say that equilibrium lies to the reactant side, or that reactants are favored. So again, if you think about the fact that you're dealing with the ratio, and if you're coming out bigger or smaller than 1, would that mean the numerator or denominator is bigger? You should be able to figure out, do I have more reactants or products at equilibrium, which is a super convenient piece of information to have, because then there's a lot of calculations we can do with that information. It gives us kind of a picture down here, representation of those. So again, this is having a really small decimal number for our equilibrium. What that would mean is that almost all of it stayed reactants, that I formed very little product in it. Now, I mentioned just a little while ago about insoluble ionic salts and the fact that we basically say that they don't dissolve. However, in reality, they do dissolve an itty bitty little bit. It just happens to be that they dissolve so little that in the grand scheme of that reaction, they stay as a precipitate. However, in this unit, we actually care sometimes about those really, really small values of product that we're making. And so in this unit, we're actually going to do some calculations with those insoluble ionic salts, even though if I was writing a balanced reaction, I would just leave it as a solid precipitate. Now, when our K gets really big, what that means is that basically everything went to products. And usually we say if K is bigger than 10 to the 5th, that the products are so overwhelmingly numerous that essentially that reaction went 99% to completion. And so at that point, we would just use regular stoichiometry to solve any amounts in that reaction. However, when I have these other situations where the amounts are kind of not overwhelmingly one or the other, where we really truly have an equilibrium present, then we're going to use another system to do those calculations instead of just traditional stoichiometry. We're actually going to use what are called Rice tables. And so you're going to get really used to seeing Rice tables here in the next couple of videos. All right, we've got a couple of examples here I want to talk about. First off, this one here had some diagrams, and it says that the following diagrams represent 3 different reactions at equilibrium. However, you notice they all had the same basic format. You had one reactant and another reactant joining together in a synthesis, all in a 1-to-1 ratio, which made it really convenient here. And so the first thing that they want us to do is, assuming that each particle drawn represents 1 mole dissolved in 1 liter, so basically 1 particle is 1 molarity, calculate the Kc value at equilibrium for each of the 3 reactions. So starting off with reaction 1 here, I noticed 2 of my products for every 2 and 2 of my reactants. So again, doing a products over reactants situation, I assume that each particle represents 1 molarity. You notice also I raised them each to an understood power of 1, and that was because the coefficients were 1. So once I did that math, that got me a value of 1/2. Now I did the same thing with reaction 2 and reaction 3. So here on reaction 2, I had 3 products to every 1 and 1 reactants. So that left me with a Kc value of 3. And in reaction 3, I had 1 product to every 3 and 3 of the reactants remaining. And so that gave me a Kc value of 1/9. So then it asks, hey, for which of these 3 reactions does equilibrium lie to the reactant side? Now, I'll be honest, you probably could have answered this question without necessarily doing all of these calculations, because I could see on both reaction 1 and reaction 3 that I had more particles present of reactants than I did of products. So it makes sense that for both of those, they lie to the reactant side. Reaction 2, however, I had more products, and so that would have lied to the product side. However, if you're ever asked which one lies further to one side or another, then you're looking for either the larger value if you're trying to figure out if you're lying more to the product side, or the smaller value if you're trying to get to the reactants. Again, you're looking for those extremes. So here, since I'm trying to figure out which one lies further to the reactant side, that would be 3 because its fraction was much smaller than the Kc value of reaction 1. All right, let's look at 2 more on the next page. So this next one here said, consider the particle diagram shown for the reaction of A going back and forth to B, where A is represented with white spheres and B is represented with black spheres. And the first question they ask us to indicate the time on the graph where equilibrium is reached. And so to answer this question, what I would do is look at how many particles I have of both the reactants and products in each of these time situations and kind of see where things start to stabilize out. Here, obviously, I have all reactant. Here I have almost all reactant with a little bit of product. Here I have, let's see, 1, 2, 3, 4 reactants with 1, 2, 3, 4, 5, 6 products. Here I have only 2 reactants left with 8 products. And then I'm like, oh wait, this one has 2 reactants with 8 products as well. And so what that means is that I've kind of stopped changing, looking overall here. I have the same ratio of reactants to products at that point. And so that would be where equilibrium is reached. It's reached at this time. And so technically both of these last 2 time frames would be at equilibrium. However, I want to point something out here, and I made a note about it here on the side. If I notice at this point in time, I had these 2 molecules as my reactants. But then as I moved to this one, this reactant right here became a product, and this product that was here became a reactant. There were still changes in those molecules occurring, even though the ratio of reactants and products remained consistent. So then it says, hey, assuming that each particle drawn represents 1 mole dissolved in 1 liter, calculate the Kc value at equilibrium. So this is where I would do my products over reactants ratio. And so again, at equilibrium, we said we had 8 products for every 2 reactants. And so that would leave us with a Kc value of 4. Now, this question here says, hey, was the Kc value bigger or smaller than 1? Well, I got 4, so that was obviously bigger than 1. And so what that would mean is that the products are favored at equilibrium, which if you look back at the picture should make sense because, hello, I had way more product here than I had reactants once I reached equilibrium. All right, one last one here. It says that, hey, we have 2 different reactions shown in the graphs below. Label the graphs with which reaction is reactant favored and which is product favored. So you notice that both of these are kind of starting off with a certain amount of reactants and products, and then we've let this reaction proceed. So over these frames here, this is where I can measure kinetics and all of that, the rates at which things are changing. And so what's happening here is that the QC is constantly changing over this time frame. That ratio of products over reactants is constantly varying. However, once I get to equilibrium here, then I would reach a stable point for that ratio. So I want to compare the ratio on these. I notice that on this one, my products at equilibrium are more numerous than my reactants. And so if products are more numerous than reactants, this reaction A must have been product favored. However, on this one, I notice when equilibrium is reached that here the reactants are greater than the products. And so what that would mean is that this one is reactant favored. So what I want us to see here is that we can tell when equilibrium is reached a couple different ways. Obviously, I could do this graphically with notating where my concentrations are stabilizing out. But I could also do this with particle diagrams where I look at my particle counts and see when those stabilize out. I could do it with numbers. If I was given some math problems, I could figure out when I've reached equilibrium. So there's all kinds of ways that we can figure out when we've reached equilibrium. It's what do we do with that information once we have it? And that's what we're going to explore throughout this Unit 7. All right, I hope you're feeling good about kind of the general idea of what equilibrium is and how to find our equilibrium constant. If you have any questions or need any help, please feel free to email me. Bye, guys.